Hello, welcome to another lecture in the course. We're going to be talking about the Wirtinger operators to give a sort of a nice interpretation of the Cauchy-Riemann equations. So this is subsection 222 in the book. All right, so suppose that, as usual, we write it as x plus iy using the real and imaginary parts. So we define these operators, d by dz and d by dz bar. And these are written as if they are partial derivatives, but really, they're just operators that you apply to functions, right? These guys, d by dx and d by dy, those are actual partial, normal, regular partial derivatives in x and y, just like in vector calculus, right? So these are not partial derivatives. They look like that because they sort of act like that, but they're not partial derivatives. They're formal operators, differential operators that you just apply to functions and you get a number. I mean, basically, right? If there wasn't this I, that would be like a directional derivative. But there is this I, so it's kind of maybe directional derivative in kind of a complex direction. But if that would make sense, right? So how do these why this form, right? Because I would have to think a little bit about how they're how they work, and sometimes this minus I sort of screws me up a little bit because it's the the z derivative has the minus I. Anyway, you can think of it as being really plus 1 over I, and then it works, right? But how are they determined is, well, we want the derivative of z with respect to z to be 1 and derivative of z bar with respect to z to be 0, right? We want these guys to be. And the same thing with z bar. When I differentiate z with respect to z bar, then I want 0. And if I differentiate z bar with respect to z bar, I want 1, right? I want them to, I want to set it up so that it's almost as if z and z bar were separate variables. Okay, so let's see how these apply to a function. So if I have a complex valued function, let me write it as u plus iv as usual, right? So what if I apply, let's say, the z bar derivative to the function, right? Well, how do I apply the x and the y derivative? Well, I apply it to u plus iv, right? So I apply the x derivative to u plus I times the x derivative I applied to v, and the same thing with the y, right? So I get this right, this expression, and I write it in terms of the real and imaginary part, right? So far, yeah, that's just how you would apply the operators, right? Now, this expression, df dz bar is 0, well, if and only if the real and imaginary parts are 0, right? I mean, it's a complex number, so it's 0 if and only if the real and imaginary parts are 0. What are the real and imaginary parts? Well, the real part is 0 if and only if I have this. The imaginary part is 0 if and only if I have this, right? Well, these are precisely the Cauchy-Riemann equations, right? These two equations we saw are precisely what we needed to have a holomorphic function, right? So, we can write down the Cauchy-Riemann equations in a simpler way, right? If I have a function f defined on some open set, that it's holomorphic if and only if it's real differentiable. So let's not worry about the, I'm going to assume real differentiable, and we have this equation, right? So this is really the Cauchy-Riemann equations right here, right? Written as a single complex equation. It's really two real equations, right? So we have the two real equations and one complex equation out here, right? But they're the same. It's the same equation. It's just written in terms of this, operator, right? And this, it makes it seem like that. This equation makes it seem like, well, a holomorphic function is one that does not depend on z bar, and in some sense, that is true, right? We'll see more of that, in just a moment, right? So, all right. On the other hand, let's look at the z derivative, and let's suppose that f is holomorphic, right? So let's suppose that f satisfies the Cauchy-Riemann equations, right? So then if we look at the z derivative, again, I just write it, I just apply it, just like before, and I group the real and imaginary parts. Then I can use the Cauchy-Riemann equations. Now, it doesn't tell me that this is 0, but, right, I can over here, I can replace this with du dx, and I can replace this with minus dv dx, right? So I have this guy, right? That's just the x derivative of f, right? Now, as long as f was holomorphic, right? That's what I assumed. That's what I used in this equality. Now, another way of writing it is I could either go from here, either go from here or from here. Anyway, apply the Cauchy-Riemann equations again, right? And get that this expression is also equal to this thing, right? Which is, it's not quite the y derivative of f. It's 1 over I times the y derivative of f, right? You really, the way you want to think of it, it's not really a derivative of with respect to y. It's a derivative with respect to iy, and we'll see why that would be. Now, if the derivative, right? I mean, if it's the holomorphic function, the complex derivative exists, right? We could compute it by approaching from any direction, right? So we start with the definition, right? And now, instead of approaching from h, just approaching anywhere, right? I mean, if this limit exists, right, I can compute it by just maybe restricting to the real line, right? So restricting to real t, right, and computing the limit that way, right? The existence of this limit doesn't imply this, right? But the existence of this limit implies the existence of this limit, and that they're equal, right? Now, what is that? Well, that's precisely, right? If I'm moving along the real axis, that's just adding to the x, right? Moving the x around. So that's precisely this guy, right? This guy over here, right? So I have the x derivative with respect to z, right? Now, if I instead of, so I'm starting with the same thing, and instead of going along the real axis, what I'm going to do is I'm going to approach along the imaginary axis. So I'll write it like this. So t is still real, but now I'm putting it it. I'm changing to y, right? Well, that's just the y derivative, right? But notice that I have, if I want to make it the y derivative, this I has to go out, right? So I have this 1 over I, and that's this 1 over I right over here, right? So that's why I get this formula, right? I get either this formula or this formula. In either case, these are equal to df dz, right? So what we have is that the derivative with respect to z, the sort of df dz, the Wirtinger operator derivative with respect to z, is equal to the complex derivative, right? For a holomorphic function, right? As long as this is a holomorphic function, right? I mean, notice that this guy over here, I can compute that for any function, well, as long as the partial derivatives exist, right? It doesn't have to be a holomorphic function. But this guy over here, f prime, only for a holomorphic function. That really what makes a holomorphic function a holomorphic function. The existence of that, right? Now, it gets a little bit, even a little bit subtler if you write f prime as df dz with the regular d's, not the curly d's, right? Because that's supposed to be, this thing over here is supposed to be the regular complex derivative, right? So that's different from the curly guy, right, which is the Wirtinger operator, right? Because the non-curly guy, the regular complex derivative, that only exists for holomorphic functions, whereas the Wirtinger operators, they exist for any real differentiable function, or any function with partial derivatives, really. Now, if you have polynomials, you can always write them in terms of z and z bar, right? You can always, substitute for the, I have a polynomial in x and y, right? And I can substitute the x and y for z and z bar, right? So I have these polynomial functions, not necessarily holomorphic polynomials, not polynomials in z, polynomials in x and y. And I can write them as polynomials in z and z bar. Now, for these guys, and it's basically just how this is defined, you have to do a little bit of work, a little bit of product rule to basically prove the power rule over here, and product rule for these guys. But you can prove that basically if I for example I'm differentiating this polynomial here, z squared, z bar cubed plus z to the 10th, right? I can just treat z and z bar as if they were separate variables. And when I apply the Wirtinger operators to them, I'm just, formally it works as if these were separate variables, right? This is exactly what you would get if you were in calculus and, you were taking, derivative with two variables, right? Partial derivatives. So it almost works like partial derivatives, almost as if z and z bar were separate variables. So holomorphic function is one that does not depend on z bar. And it's you can see it over here. For example, this polynomial is not holomorphic. Well, why? There's a z bar in it, right? The only time that you're going to get a holomorphic polynomial, one that is just a polynomial in z, is going to be precisely when the z bar derivative is 0, which means precisely when you expand the polynomial, there are no z bars left, right? So you can actually check that a polynomial is holomorphic by just algebraically, by writing it in terms of z and z bar, expanding everything, and showing that all the z bars actually cancel out. Right? So again, sort of this caution for this polynomial, the ddz does not exist, right? I mean, doesn't make sense to compute this, right? I mean, or you could say does not exist, right? I mean, the complex derivative does not exist, right? However, this derivative, sorry, it's not the complex derivative, it's the Wirtinger operator. That guy exists. right? That only depends on the x and y partials, right? So that I can compute. I can always compute, right? As long as all the x and y partials exist, right? So that's that's a little bit of a subtle issue, right? So for holomorphic functions, the functions where the z bar Wirtinger operator is 0, the z Wirtinger operator is the same as the complex derivative, right? For other functions, the Wirtinger operators exist, but yeah, if the function is not holomorphic, it's not complex differentiable, then you can take the complex derivative, right? Right. Several other remarks. These are left as exercises. So if we write the real derivative, the derivative of f as a function from R2 to R2, which is a 2x2 real matrix or a real linear operator on R2 or real linear operator on C, we can always write it in this form where zeta and xi are just some complex numbers, right? Now, if you write it in that form and you take the Wirtinger operators, then at that point P, you get the zeta, that's the z derivative, and the xi is the z bar derivative, right? And so if you remember from the section on Cauchy-Riemann equations, you had that basically a function was holomorphic if and only if the derivative looked like this, right? Meaning that xi was 0, right? Just precisely is what we're saying, right? If f bar is the complex conjugate, then if you compute the Wirtinger operators, so if you take the complex conjugate of the z derivative of f, it is the same thing as the z bar derivative of the complex conjugate of f, right? And similarly, if I take the z bar derivative of f and conjugate that, that is the same thing as the z derivative of f bar, right? And this is, there's nothing deep about this. This is just, you write down the definitions and it just works out, right? And that's exactly what it comes out to. Now, finally, and this is maybe the hardest one of these, is if you write down the chain rule in terms of Wirtinger operators, it actually comes out as if you had really a function of two variables, z and z bar. So this is chain rule for not necessarily holomorphic functions, right? Any real differentiable function will satisfy this chain rule. And it's basically writing the real derivative, this df, writing it in terms of the z and z bar derivative, basically doing this. And so if you write out what it means, it means exactly what you would think it would be if they were separate variables, right? So if I'm composing g and f, right, and I differentiate with respect to z, this is the Wirtinger operator, then that's the same thing as differentiating g with respect to z, but then I'm thinking of plugging in f for the z, right? So then I have to differentiate f with respect to z. Plus, I have another variable, I have z bar, so I have to differentiate g with respect to z bar. Now, z bar is really f bar, right? So I also have to differentiate f bar with respect to z. All right. Same thing for the z bar, except, over here you get the z bars, right? Okay. So that's Wirtinger operators and how they work. I mean, we won't maybe use them all that much. Every once in a while they're nice, but they basically give you sort of a nice way of thinking about the Cauchy-Riemann equations. and they become a lot more important, let's say, in several complex variables than in one complex variable theory. But you can, a lot of stuff that's written sort of more classically, you can write in terms of the Wirtinger operators, and it becomes a lot nicer, actually. All right. So next time we're going to look at the inverse function theorem, and so see you next time.